Hey, in our last video, we looked at approximating the area under a curve. It's time to do better and come up with an expression that gives us the exact area under a curve. So we start with a curve, y equals f of x, and 2 points a and b on the x-axis. And we've seen that we can approximate the area between the curve and the x-axis from a to b by dividing the interval from a to b into rectangles, the heights of which are governed by the function value at some point between the left and the right endpoint of each rectangle. It might be the left endpoint, might be the right endpoint, could be the midpoint, could be some other point, so long as it's between the left and right endpoint of the rectangle. And if we divide the interval from a to b into n rectangles, then the width of each rectangle is b minus a, the distance from a to b, divided by n, and we'll call that width delta x, or the change in x. And if we label these rectangles a1, a2, a3, etc., then the area of the ith rectangle, a sub I, is just the width times the height, or f of x sub I times delta x, where x sub I is just some point between the left and right endpoints of the ith rectangle. And adding those areas together, we get an approximation for the area between the curve and the x-axis. It's a1 plus a2 all the way up to plus a sub n, which is the same thing as saying f of x sub 1 times delta x plus f of x sub 2 times delta x all the way up to f of x sub n times delta x. And it's convenient to write this in what we call summation notation. That's a capital Greek sigma there. And we read this as the sum as I goes from 1 to n of f of x sub I times delta x. And it's equal to just exactly the expression that you see to the left of it. Okay, here's the punchline. We've seen that the more rectangles you use, meaning the larger you let n become, the better the approximation is. And so it makes sense to define the exact area under the curve to be the limit as n goes to infinity. In other words, the limit as you go to taking infinitely many, infinitesimally thin rectangles, so the limit as n goes to infinity of this sum of the areas of these rectangles. And if this limit exists, then we call it the definite integral from a to b of f of x with respect to x. And the notation for it is as you see right over here. So you can think of what we've been doing recently with Riemann sums as a matter of approximating definite integrals. It's also very important to understand that the definite integral is a number, as opposed to the indefinite integral, which is an antiderivative, which is a function, or more precisely, an infinite family of functions. So very, very different. Just a little terminology before we move on. If this limit exists, then we say the function f is integrable from a to b, meaning that it can be integrated. The function f of x here is called the integrand. It's the thing that you're integrating. And these numbers a and b are called the limits of integration, or sometimes the constants of integration. Okay, let's look at an example. The integral from 5 to 7 of x minus 2 with respect to x. And just getting a quick picture, the line y equals x minus 2 is a line with slope 1 and y-intercept negative 2, and we're talking about the area under this curve, or under this line, and above the x-axis from 5 to 7. And the beauty of this particular example is that we can actually compute this area. It's a rectangle with a triangle sitting on top of it. And the rectangle has width 2 and height 3, and the triangle has width and height both equal to 2. And so using the width times the height as the area of the rectangle and 1/2 base times height as the area of the triangle, you do a little arithmetic, and you find that this definite integral is equal to 8. And notice that we didn't do any calculus. Eventually there will of course be calculus involved, but at the moment we don't know how to do the calculus. This definite integral is defined in terms of the limit of some infinite sum, and at the moment we have no idea how to compute that limit. On the other hand, we can say something about when this limit exists. We have this theorem. If a function f is continuous on the closed interval from a to b, then it's integrable on the closed interval from a to b. Which is just another way of saying that the definite integral from a to b, which is defined in terms of this limit as n goes to infinity, of the sum I equals 1 to n of f of x sub I times delta x, that limit exists. Okay, I'd like to look at some of the properties of the definite integral. Suppose that instead of looking at the integral from a to b of f of x with respect to x, we look at the integral from b to a of f of x with respect to x. So I've interchanged the constants of integration. We had originally that delta x was b minus a over n, so if you switch the a and the b, then you get that delta x is a minus b over n. And we can write that as negative b minus a over n, which is to say that if you interchange the constants of integration, if you switch their order, then delta x changes sign from positive to negative, or maybe from negative to positive. Either way, it changes sign. And so each area, which is the height, the function value, times delta x, also changes sign. And that gives us this very important property of the definite integral. The integral from b to a of f of x with respect to x is equal to the negative of the integral from a to b of f of x with respect to x. We also get from the properties of limits that the integral from a to b of the sum of two functions is the sum of the two integrals. The integral of the difference of two functions is the difference of the integrals, and the integral of a constant times a function is the constant times the integral. You can pull the constant outside of the integral. So all these follow from the properties of limits, and they're completely analogous to the properties that we found for indefinite integrals. You have seen these before. Here's one that's a little bit more interesting, and I'll show you a picture in a second. It says that the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And the basic idea is this: there's really no reason not to split the area under the curve from a to b at some point in the middle c and just add it up as two areas. They add to the original area. So that's the basic idea. Actually, it is slightly subtler than that. And the thing that's subtle and perhaps even a little bit beautiful about it is that nowhere in that rule did it say that the c has to be between a and b. And in fact, it doesn't. Here I've shown the area under the curve between a and b. And here's the area under the curve from a to c. And in orange, I've just shaded the area from b to c, except that's not what the integral says. The integral says the integral from c to b. And the integral from c to b is the negative of the integral from b to c. And so what we're doing is we're taking the area under the curve from a to c and subtracting the area under the curve from b to c. And that indeed does give us the area under the curve from a to b. And the last thing I want to show you is this picture here. Up until now, we've only been looking at curves that were always positive, always above the x-axis. But the definite integral is defined in terms of sums of areas of rectangles, and the rectangles that are in this region right here all have heights which are negative. And so, the areas or the computation of the definite integral here includes a delta x, which is a positive number, times an f of x sub I, which in all this region is always going to be a negative number. And so it's possible that there's some cancellation, some positive number here with some negative number in here. And it looks like just from this picture that the definite integral, if we computed it from a to b of this function, would actually turn out to be a negative number. Perfectly reasonable. The definite integral is a number. We started looking at it in terms of areas under curves, but it doesn't necessarily have to relate to an area. I mean, it has some relation to an area, but it doesn't have to precisely be the area. Okay, one thing that should be on your mind right now, and perhaps somewhat disturbing, is that we have these two different things that we recently learned about. The indefinite integral, which is a matter of antiderivatives, and the definite integral, which is something like a matter of area under curves. And they're both given very similar names and extremely similar notation, and yet they seem to have absolutely nothing to do with each other. And so that is disturbing. It would seem unnecessarily cruel and confusing. And so we would like to hope that the definite integral and the indefinite integral are in some way related to each other. And that is where we are heading next. In the meantime, there's a homework on the definite integral. Take a stab at that, have some fun with it, and I look forward to seeing you in class.